Hey Math 1, I'm back with one last look at the substitution method, and then I'm going to tag along with that to show you maybe a more convenient method, certainly a completely different approach to solving linear systems without graphing and without substitution method. So what I gave you guys here is a linear system in which there doesn't seem to be any convenient variable to solve for. It's like no matter what you do, you're going to get fractions if you divide both sides of either equation by either the x's or the y coefficients. So what I did was I said, okay, if we're going to check out substitution here, let's just choose the equation with the smaller numbers, x being the smallest one, to get by itself. So I chose the top equation, okay? I solved for x, and I got these fractions. Now, I kept the 29 over 3 as such and didn't convert it to 9 2/3 like I normally do. From there, in fact, I usually put parentheses around here just so I don't forget to multiply by that number, that coefficient that is by x in the other equation. Step 2 means I have to pick the unused equation, which is 6x plus 5y equals 43. And I keep in mind this concept of the black x and the blue x are the same value. So sometimes putting them as the same color sort of gives us that visual cue that, oh, that can be replaced with parentheses 29 over 3 minus 4y over 3. So that's what we're going to do. 6 times the quantity x, 29 over 3 minus 4y over 3, okay, plus 5y equals 43. Now, compared to all the situations we've seen before, this is kind of a mess. You guys can use calculators now, so that's a great tool to have in your back pocket. But just still recognize that you can take 6 times both parts really without a whole lot of trouble. The 6 is going to cross-cancel with both 3's to give you 2 times 29, 58, and 2 times 4y, which is negative 8y with the minus there. So, we now just get the constants to the right-hand side, combine the two y values on the left, and fortunately for this example, we do come up with a whole number answer for y. Y is equal to positive 5. Now, once we get step 2 taken care of, step 3 takes our answer from here and says the equation that we picked in step 1 should be the most convenient value by which to solve for y. Did I say y? I meant x. So y equals 5, that y right there. So if I have x equals 29 over 3 minus 4 times 5 over 3, that'll give me my x value. Turns out this is a whole number too. X equals 29 thirds minus 20 thirds, which equals 9 thirds, which is 3. So remember, y equals 5, x equals 3. We want to make sure that we put it as an ordered pair just to solidify the fact that these are two lines that are intersecting at the point 3, 5. Okay, yeah, so as you can see, substitution can get a little bit excessive with the amount of work that needs to be done, not only getting the first step done, but the second step as well for solving. This new method that I'm going to show you guys helps eliminate some of that work by eliminating one of the variables in step 1. So let's check that out. So what is this new alternate method that I'm speaking of? Let's get a little closer here. Well, this new method requires one thing. We need either the x values to be twins, so essentially the same number, to be, I'm going to put twins in quotes because I'm using a very loose term for twins here, to be twins or the y values to be twins. That just means the same coefficient for x or for y. So, as I look at 3x plus 4y equals 29, and I look at 6x plus 5y equals 43, I'm asking myself, is there anything I can do to one or both of these equations to make the x's the same or the y's the same? And again, we're looking for convenience here. Which of these seems to be the easiest to work with? I think we can make both of the x's 6. If all I do is multiply the top equation, both sides, by 2. In fact, I'm actually going to multiply by -2. Instead of regular twins here, I don't want identical twins. I want a good twin and a bad twin, a minus 6x and a positive 6x, because it's going to make simplifying things in the next step easier. So when I multiply everybody by -2 here, here's what I get. I get -6x minus 8y equals -58. And on the bottom, nothing has changed so far. Now, if I have one bad twin and one good twin, a -6 and a positive 6, adding each column will give me a new equation, a new relationship between the x's, the y's, and the constants, in which the x's have completely disappeared. So, I'll use a new color because this is completely different. If I, again, add the columns, the x's completely cancel out. -8 plus 5 is -3y. -58 plus 43 is -15. And I get down to one of the variables almost completely isolated in 2 very short steps. Now I just got to divide by -3, and I've got y equals 5. So I needed to look at this from a completely different perspective. Instead of getting x or y by itself, I said to myself, I need the x's to be the same or the y's to be the same. And I'm going to manipulate it as a negative twin with a positive twin, and that'll get me one of the variables right off the bat. Okay? Now, I'm not done yet because this only gives me the y value coordinate. I now take this, and there's no specific step where I plug into. I just go back to the originals and say, which of these would be the most convenient for me to plug in for y? And at this point, it's like I could pick either one of these and it's not going to be a monumentally different outcome. I'll just pick the top. So 3x plus 4y equals 29. Instead of y, I'm going to put 5. And then I solve that equation. 4 times 5 is 20. I can get the constants to the right and then solve for x. X equals 3, y equals 5. Completely different method, but I got to the solution. I personally think that for this particular problem, this alternate method, which we call the elimination method, we eliminated a certain amount of work with fractions, and we eliminated one of the variables on the first step. That's why we call it elimination. So, I'm going to stop the video right now, and then in the new video, show you guys the examples. So, check out that second video on 7.3.